Hi guys, thanks for tuning in. Today we're just going to be covering some techniques for solving logarithmic equations. So I'm just going to go through a couple of examples. Most of the stuff is not necessarily new. It's just more of a review of all the things we've done so far and to help you consolidate looking at the different methods. So to start with, we're going to take a look at a couple of these prompts. Just as a few reminders, an extraneous root is a useless solution, one that we cannot use. How can you identify if it's an extraneous root? Well, you can actually just see if the solution works in the original equation. And if it results in an invalid answer, then it's no good. An example of an extraneous root could be something very simple. Let's do 2 to the x is equal to -3. And like we said, there's no value of x we can ever raise 2 to result in a negative number. This would also look in logarithmic form like this. The log base positive number of a negative number is equal to x. And right there we can see that you cannot solve this. You can also punch this into your calculator and you will see an invalid answer. It'll say undefined, or it will just say no thank you, and your calculator will be upset with you, and life goals are to never have that happen. Now, if we actually want to solve and find the roots of these equations, again, remember the roots of the equation are just finding the values of x that satisfy the equation. So we're going to start by using algebraic reasoning. The first things first, remember when there's no log base specified, it is a common logarithm, so it's a base of 10. I'm just going to add that in for you guys. And let's use some algebra to solve this. So the straightforward way is to apply the definition of logarithms. Remember, the base to the power of the opposite side of the equal sign is equal to what's inside the log. So if we rewrite this as 10 to the power of 1 is equal to x plus 4. It's very, very straightforward to actually solve this, because now we just subtract the 4. 10 to the 1 is just 10, and we get x is equal to 6. Not super duper challenging. If we had to use graphical reasoning, though, we should think about how we're going to graph this. So we've got y equals the log of x plus 4. And to graph this, we're going to graph two things. We're going to graph this function here, and we're going to graph the other side of the equation, which is y equals 1. And we'll just see where they intersect. And that's pretty straightforward. So let's take a look. The original log function, y equals log of x, that's base 10, has a couple of key points and features we should be aware of. That will translate to, well, we can see this has been shifted to the left by 4 units. So let's take that into account. So we would have to subtract 4 from our x coordinate and leave y alone. So that's what we're going to be doing to all our key points. Remember, the key points are simply the x-intercept, which is 1, 0, and the point that is at the base and 1. In this case, the base is 10. And finally, we have the asymptote, which is x is equal to 0. So let's translate each of those. So we're just going to subtract 4 from the x coordinate, so we get -3 and 0, and subtract 4 from 10 to get 6 and 1, excuse me. And now let's graph those key points. Oh wait, we need to move the asymptote, so we're going to subtract 4 from that as well to get x equals -4. So graphing at x equals -4, there's our asymptote, dotted line. Graph our key points, -3, 0, and 6, 1, right there. There it is. And we should be labeling these points. So -3, 0, 6, 1, and x equals -3. And then we just graph the line as best we can, the curve that is, as best we can, passing through those points and not touching the asymptote. And of course, we label the graph, y equals log of x plus 4. And then the second thing we'd actually have to graph is x equals 1. and that's just a y equals 1, that is, and we're just going to go straight through there. And why are we graphing y is equal to 1? Because that's the right-hand side of the equation. We graph the left-hand side with the curve, right-hand side with the 1, and then we just see where they intersect, and they intersect right here at 6, 1. And so then we can just say the POI is 6, 1. And so the root is actually the x value that makes that happen. Therefore, the root x equals 1 is our answer. Okay, so that's a very effective means of doing it. Let's do another couple of examples. We'll use mostly algebraic reasoning as it is the most directly solvable. So the algebraic reasoning for this one, we're just going to apply the definition of a logarithm. And we're going to write 5 to the power of 2 is equal to 2x minus 3, which actually results in a very easily solvable equation. There it is. 5 squared is 25 equals 2x minus 3. Add 3 to get 28 equals 2x. Then divide by 2 to get x is equal to 14. And there's our root. Let's try another example on the next page. Once we're done these two, you guys will have a lot of time to practice. So these ones can be a bit tricky. I mean, they look a bit scary, but the trick to these is to remember that we need to kind of put everything together. We need a single log equals to a single number, and then we can actually apply the definition of a logarithm. So we're going to start by moving the log to the left-hand side, and we'll move the -1 to the right-hand side, resulting in the equation log x minus 1 plus the log of x plus 2 is equal to 1. And then we're going to apply that rule of logarithms. When you're adding two logarithms, it is the same as having the product of what's inside them inside one logarithm, called the product law. So apply that product law to result in the log of x minus 1 times x plus 2, all inside there. And that's all going to be equal to 1. I'm going to expand the quadratic inside, because why not? And that gives me x squared minus, plus x minus 2 is equal to 1. And then I'm going to apply the definition of logarithms. Again, remember, this is base 10. So it's going to be 10 to the power of 1 is equal to x squared plus x minus 2. Move the 10 to the other side, so it's all equal to 0. X minus 12. And now we factor it again and look at our two different roots. And this factors to x plus 4 and x minus 3, giving us two possible answers, x equals -4 or x is equal to 3. And now we have to test each of them back in the original answer, because if we actually pop these into the original equation, what we'll find is that some work and some don't. So we will pop the x equals 3 into the original equation to get the log of 3 minus 1 is equal to negative log of 3 plus 2. And this works out to be the log of 2 minus 1 equals the negative log of 5. And we'll notice there's nothing shady happening here. Everything works. They're both positive inside the logs, so we're good. This answer is acceptable. If we do the same thing with the -4, however, we get the log of -4 minus 1 is equal to the negative log of -4 plus 2. And we'll see in the next step, we have the log of -5 minus 1 is equal to the negative log of -2. And you'll see both of these guys are negative. And so we reject this answer. It is an extraneous root. So no, x equals -4. Let's do this one more time with this final example. And what we're going to do is we're going to start by rewriting this cube root as an exponent. So this is the log of x squared plus 48x, all to the power of 1/3. And I'm going to finish this one in a short continuation video.